can actually contribute to answering, not the first one. So we're looking forward to talk. And Margaret Fael on the Friday, we'll be talking about causal properties of narrative explanation. We're also looking forward to that talk. On Friday, and after that, we'll have a week of break, so it will be a spring break, where we say a week without work. Today, it's my pleasure to introduce or reintroduce Marta Bielinska, who is a postdoctoral fellow, as you know, at the Center for Philosophy of Science. She got her PhD at the University of Oxford before she got two master's degrees, a BPhil in philosophy and a Master of Science in Mathematical and Theoretical Physics. And before, she was at another graduate at, I'm going to butcher the name as usual, Jagiellonian University. Close enough?
Yes. Actually, I have some photos.
Right.
But no spoilers.
And what I have to you, she's published in philosophy of physics. She has a paper coming out to study philosophy and history of science about hidden symmetries in physics. She also has published in Foundations of Physics. She also has published in the history of physics. She has a paper on Laplace as well, published in Photons. So she's published widely in the history and philosophy of physics, as you can see. Now, my true mission right now is not to tell you about her, to tell you about Poland and Central Europe.
Thank you.
It's been a very sore point for the whole year that actually Poland is not in Eastern Europe, as you might have believed. And as I made a mistake to say this morning, it is in Central Europe. All right, Eastern Europe starts at the border of Poland, on the other side. All right, it's a very important point, so I want to make it clear. Okay? Don't make that mistake. You're not allowed anymore. Now you know.
Thank you.
Thank
you for this lovely introduction, and thank you for giving me an opportunity to present this work. So as Edward mentioned, I work nowadays mainly on philosophy of physics, but I do have a project that I've been thinking about since the beginning of my undergrad. And I'm really happy that I can finally present what came out of these years of thinking about this. So let us go back a few years into the past to Krakow, where little undergrad Marta was studying for a degree in philosophy and a degree in theoretical physics. So that's philosophy faculty in Krakow. And as a part of my philosophy degree, I joined a reading group on laws of nature. And let me say, it's been a really lovely course. And we've been reading Armstrong and Baird and Lewis. And at that time, everything made sense to me. I would believe in everything I've read. But the more I've been reading the philosophical literature on the laws of nature, the more I felt that it is completely detached from what I'm being taught in my physics, as a part of my physics degree. And I do very vividly remember one of the first classes when we've read Dretske and his discussion in which he talks about laws of nature in terms of F-ness implies G-ness, thinking, goodness me, if everything that there is there to laws of nature is just an implication that you can formalize in first order logic, why is my physics degree so hard? Why do I need to go through the terror of linear algebra and calculus and differential geometry? And then I need to learn about all those abstract entities like manifolds or fields if everything boils down to F-ness implies G-ness. So don't worry, since then I grew in wisdom and I've learned to acknowledge some subtleties in philosophical accounts of laws of nature. For instance, that the fact that the claim that laws are based on relation F-ness implies G-ness doesn't necessarily imply that all laws can be rewritten into an implication in first or higher order logic. And actually, I've also learned that if you really want, you can formalize a significant part of contemporary physics into algebra and into the language of logic. But one thing hasn't changed, and that is that whenever I read a paper in philosophy of laws of nature, I feel that the examples that are employed are very far from what we are being taught during our physics degrees and what physicists do in their day-to-day work. And actually, when I was reading more and more on philosophy of laws of nature, I realized that I'm not entirely alone in this impression that the philosophy of laws of nature should turn more into the side of scientific practice. And here I gave you some names of philosophers who've talked about the laws of nature and scientific practice, specifically in context of the best system account, which is the topic of the presentation today. Why this specific account rather than, for instance, Dretske that I've mentioned before, it will become clear very soon. these authors mean by scientific practice very different things. I just wanted to flag it in the very beginning. I will go back to this point later on during the presentation. So I've already covered the motivations, and now I want to move to a bit that will be very obvious to some of you, but also I want to acknowledge that not everyone participated in a reading group on laws of nature on their first year of undergrad. So I want to present to you the landscape of views on laws of nature in the contemporary literature. And then I want to introduce the best system account. Specifically, I will focus on two aspects of the best system account, which we'll see later on that is quite important for my arguments. And then we'll move to the very heart of this paper, which is first, some reasons why the best system account can be appealing from the perspective of scientific practice. And then I want to mention some problems that I see with this approach. Okay, so let's start with the landscape of views. And to make it a bit more fun, let's phrase it as a quiz. So by the end of this slide, you will know what sort of a philosopher of laws you are. So the quiz is based on two questions. The first question is, do you believe that laws of nature, at least in some sense, exist? And if you give a negative answer to this question, you probably support the so-called no-laws views. And you're among such authors as Van Frassen or Cartwright or Giray. So these authors are suspicious of the idea that there is a privileged class of metaphysical laws of nature. And you may worry, how is it supposed to work? Like physics seems to be all about laws of nature. But for instance, Van Frassen argues that from a constructive empiricist standpoint, and for him, the aim of science is empirical adequacy rather than uncovering deep, unobservable structures like governing laws. So in particular, he thinks that we don't have good epistemic reasons to believe in laws as robust entities, and we only need new theories that save the observable phenomena. Now, if you gave positive answer to the first question, here is the second question to you, which is, do you believe that laws of nature somehow govern the world, or are they just a way of summarizing what happens? Again, if you went for the first option and you think that laws of nature govern the world, you support the governing view. And here is a whole variety of views. So for instance, if you link laws of nature with some kind of necessity, you're probably Dretske or Armstrong, then Maudlin supports a view that laws of nature are somehow primitive. Then you have dispositionalist accounts, according to which laws of nature are somehow encoded in nature of things, and so on and so forth. And finally, the view that is the most interesting to us today is the so-called non-governing view. And somehow contrary to the governing view that I've mentioned here, it's less so an umbrella term. So that's what I mean by umbrella term, that among the governing view, we had so many various, like such a big variety of what laws of nature can be. While on the non-governing view, those philosophers really were or believe that they develop each other's accounts. So it originates from Mill, and the account was developed by Ramsey. And finally, the version of the best system approach that I'll discuss today is based on Lewis's development of Mill and Ramsey together. So what is exactly the best system account? As I promised to you, I want to present it as consisting in two aspects. And the first aspect is related with the so-called Humean mosaic and related to this Humean supervenience. So what is a Humean mosaic? Well, Humean mosaic is a version of an account or like a way of seeing the world, that's the best phrasing, as a vast mosaic of local matters of particular fact, using David Lewis' words, just one little thing and then another. So if you ask David Lewis what is out there, the answer is local matters of fact. You may worry, David, you wrote so much about causation and necessity and chances. If they're not out there, where are they? And the answer is, well, these notions supervene on Humean mosaic. And crucially, laws of nature do supervene on this Humean mosaic as well. This is for the background because the notion of Humean mosaic will be quite important for us in the arguments later on. I will not talk much about supervenience. Feel free to disagree with Lewis. This is not as important as the Humean mosaic itself. So that's the first component of the best system approach. And the second component is the very definition of a law of nature itself. So this is a fairly long quotation from Lewis, but it's a very good summary of his view. And I think it's instructive to read it together, sentence after sentence. So David Lewis, in his exposition of laws of nature, starts by saying, take all deductive systems whose theorems are true. So first, we already see that for Lewis, laws of nature are elements of deductive systems. So they are not dispositions, not thoughts of God, right? We are at the level of propositions. What does it mean that theorems of deductive systems are true? Well, that they correspond to something among the local matters of fact. We do not have elements of deductive systems about unicorns because there are no local matters of fact about unicorns. Then famously, Lewis moves on to saying that some are simpler, better systemized than others, some are stronger, more informative than others. And then he again famously said that these virtues of simplicity and strength compete. And an informative system can be very simple, and an unsystematized computing of miscellaneous information can be very informative. I will show you some examples of this on the next slide. And now, crucially, the best system is the one that strikes as good a balance as truth will allow between simplicity and strength. How good a balance that is will depend on how kind nature is. And finally, we have the definition that a regularity is a law if and only if it's a theorem of the best system. So let's see how it works on some particular examples. So here I just rewrote his definition in the more concise form. So one of the pathologies that can happen when you formalize it, when you have a deductive system that describes the world, is that you can have a highly uninformative system, as Lewis says, and you just take all tautologies. It's very simple. It's not very strong because it doesn't tell you much details about the world. Second pathology is what Lewis calls an unsystematized compendium of miscellaneous information. And one way of doing this is basically take every single particle at each spatiotemporal location at every time and give a complete description of it in terms of mass, charge, and so on and so forth. So the way out from Lewis, well, his account is meant to work, rule out these two pathological examples by striking the best balance of simplicity and strength. So for instance, you can imagine that you compare two systems, like a system of truths about the physical world, all laws of physics, take all of your favorite handbooks, and in particular handbooks that contain Schrödinger equation, and then consider another system which is exactly the same but doesn't have Schrödinger's equation. And then you can ask which of these two is the best system. And the answer is probably that it is the first one, because if you get rid of Schrödinger's equation, your system loses some strength that you get from this particular equation. Therefore, because this is the best system and Schrödinger's equation is an element of this best system, it is a law of nature. That's how it's supposed to work. Why is this talk about the best system approach rather than some other account of laws of nature? So it has been argued by many philosophers that it is actually quite appealing for scientists from the perspective of scientific practice. And for instance, in a very influential paper, Cohen and Callender mentioned that one of its virtues is that it well reflects an intuition that stands behind all of science, which is to try to find theories that are both simple and strong. And to support their view, they cite Feynman. So you probably remember that Feynman was one of those famous physicists who wrote many books, like handbooks to physics. And literally in his first book, on one of the first pages, he says something like that it is possible to condense the enormous mass of results to a large extent, that is to find laws which summarize, yada, yada, yada. So this quotation is taken a bit out of context, but I see why Cohen and Callender wanted to cite it. According to them, on this quotation, Feynman says, the purpose of physics is to take this enormous mass of results and somehow summarize it. And this is the simplicity and strength that they see. And I think it's a very good point. I just wanted to give some of my examples on how you may think of this. So some people famously believe in the theory of everything. One way of thinking about this is that one day we'll have a theory from which you can recover not only all laws of physics, but also all laws of biology and so on and so forth. And just the very strive of this is supposedly like reflecting also an intuition behind the best system approach. Then, of course, obviously, we are not looking for quantum gravity to strike the best balance of quantum and gravity. It is because our quantum mechanics is not very good with gravity and vice versa. But actually, once we have quantum gravity, we can expect that it will strike a better balance than quantum mechanics and gravity, general relativity separately. And another way of thinking about this is, I want to illustrate by recalling Maxwell equations. So if you look at historical papers by Maxwell, you will realize soon that what we now see as 4 equations initially was around 14. And obviously Maxwell didn't know the operator, the notation with nabla operator. So his equations were very long. We'll actually see some examples later on. So one may think that the very reason that physicists develop notations that are meant to be more concise is, again, somehow well reflected by this best system approach's strive for strength and simplicity. The second advantage, I actually haven't found it in the literature, but this is the thing that keeps coming up the most often when I talk to people why do believe in the best system approach, and I think it's a very good argument. So when you look at the governing approaches, they all believe in some shady entities like dispositions or powers. And physics is not about this. And I gave you here an example. So imagine that I throw a rock, it falls on Earth. And if you ask a physicist, he's very unlikely to give you the answer that a rock fell on the ground because it has a disposition to be at the center of the Earth, unless he's Aristotle. But contemporary physicists would say that a rock fell on the ground because it is in the gravitational field on the Earth. So again, our contemporary physics is not based on such categories. So someone can say, well, it's very appealing for the physicalists. Something that I haven't seen in the literature, but I think is also a very important point, is that laws of nature on the best system account are propositions, which I was trying to emphasize from the very beginning. And again, if you take Feynman's book, what you see there are propositions. Okay, physicists can privately believe that laws of nature are thoughts of God or whatever, but the way in which they practice physics seems to suggest that they think of laws as propositions. And again, that's a virtue of the best system approach compared to dispositionalist accounts and so on. There are also other advantages of the best system approach that I wanted to acknowledge here. These are minor points, but I think they are really important. So in my very general introduction, I was complaining that in physics degree, you need to learn all of those sophisticated concepts. And indeed, people who work in the best system account put a lot of effort into developing certain things that are used in physics within the best system approach. So you have versions of the best system account that involve probabilities, famously developed by David Lower, but also most recently, and I find it quite impressive, Friend, Higgs, and Dewitt put a lot of effort in trying to describe how a humanist can think about symmetries, which are very central to physics these days. Then Cohen and Callender acknowledged that actually our best system, or our better best system, as they call it, version of laws of nature should account for laws of special sciences. So that's also important as a part of scientific practice. Then we have the whole pragmatist turn in humanism. People say that we should also acknowledge epistemic limitations of scientists at a given time. Right, there are laws that used to be considered as laws and are no longer are. So there are people who also addressed this and showed how you can make it work within the framework of humanism, obviously dropping some assumptions, but still within this domain. And we have a huge discussion about quantum mechanics, how to make it work, and whether you can make it work with humanism. So let me just say, people put a lot of effort to acknowledge that there are non-trivial things about physics that should be taken into account in the best system approach. So where is the problem? Why am I giving this talk to you? Well, because I think that one of the things that has been really missed in the literature is that once you literally take the same page that is cited from Feynman's book in the paper by Cohen and Callender, and if you read carefully, you will see that Feynman carries on to say, the correct statement of the laws of physics involves some very unfamiliar ideas which require advanced mathematics for their description. And then obviously he moves on to pages and pages of advanced mathematics and derivations that are, again, developed in this very abstract mathematical notions. And so my question is, are laws of physics that are actually used by the physicist, I gave you a few random examples, are compatible with the best system account? Now, one disclaimer and one note. So my disclaimer, you've probably already realized this, but I will use examples from the domain of physics. That's not very good for inclusivity, but it's fine for my argument because I'm trying to find counter examples to the best system account, so I can find them in whatever discipline. I know physics, so I use physics. Go back home and try to do this exercise with your own favorite discipline. And then the second note is to people who've been already falling asleep thinking, oh my God, another talk in philosophy of physics. I'm not going to understand anything. No one said ever. You don't need to understand what these equations mean at all to follow my points. So stay tuned. Okay, so I wanted to mention one more disclaimer here, which I think is a concern that can be shared by you if you thought about this for less than 5 seconds. So you may worry that the best system is not even in principle compatible with the scientific practice because Lewis talks about deductive systems. And when we think about deductive systems, we normally think about things, expressions that I've mentioned before. So if you open any paper on laws of physics, most likely it will contain something like this. And then obviously there's a whole debate. What do you mean by this R, or is it a necessity relation, yada, yada, yada. But even nowadays, people still think of laws of nature largely in terms of first-order logic. Well, again, the Schrödinger equation clearly doesn't look like an implication in first-order logic, at least not in this form. Is it a problem? No, it is not a problem because it's in principle possible to have deductive systems with equations. So the only requirement for a deductive system is that it has to be, its element has to be written in the formal system. So if you think that like algebra, calculus, and so on are formal systems, and I know that not everyone agrees with this, I'll come back to this minor point towards the end of my talk. If you believe in this, you don't have this problem. That's why I said, solution in the quotation marks, because there has never been a problem. Now, under normal circumstances, I would move now to some problems with the best system account, and this is a very relevant information to those of you who are watching us online. I'm in the room with some excellent general philosophers of science, some of whom worked in the field of scientific practice. So I can see in their eyes that they're ready to ask me in Q&A, okay, that's really nice, but like, where is the scientific practice here? What do you mean by scientific practice? So let me address this. Let me address my lovely colleagues at the center. So what do I mean by a scientific practice? And I want to understand by this basically that I will be on the next few slides, and for the rest of this presentation, I'll be taking examples from the best system approach. Sorry, I'll be taking examples of laws that are actually used by physicists in their labs, in their papers, in their handbooks, in the form in which they are used by contemporary physics, again, for instance, in the form of mathematical equations, and see whether there are also laws on the basis of the best system approach. I appreciate that in the literature, like general literature on scientific practice, it's a way more sophisticated account. You talk about theorizing and creating models and so on. I know that this can be a bit underwhelming. Let me say, if you think that I'm bad and imprecise, other people are even worse. So I started my presentation with recalling like Cohen and Callender, Friend, and so on. Like, there are people in this literature who talk about scientific practice, and each of them means something slightly different. So for instance, Cohen and Callender, basically, when they say that our laws of nature should be more adequate for scientific practice, they mean that our laws of nature should account for special sciences. Or on other account, people consider scientific practice as a need to acknowledge that we had some scientific limitations and certain laws were discovered later on, and some laws turn out to be false. So you may wonder, why couldn't I just say, phrase this problem as, is the best system approach compatible with laws of nature, if it seems that that's what I'm planning to focus here on? By the way, this is a digression. Like, if you are not very triggered by me saying scientific practice, it's probably not very important for you, but let me explain myself, okay? And the reason for this is that you will see very soon that when we move to problems with the best system approach, the structure will be the following. Let's take an example of a law used by physicists. Usually it will be a form of equation. Then we conclude when we apply it to the best system account, it turns out that it is not a law and there are some problems with considering it as a law in the best system approach. And if I pause here, someone could say, oh, you just proven that laws are, as equations, are incompatible with the best system approach. But why should laws at the first place should be equations? Why should we believe that laws of nature are equations? And my answer is, I care about this because this is what physicists do. And as long as you buy into my introduction in the very beginning, saying, well, it would be nice if laws of nature, as they're used or defined in by philosophers, would be somehow relevant or similar or ideally the same as the laws of nature as are used by physicists. To say this, I decide to talk about scientific practice, which I understand in this very specific way. Okay, I'm waiting for the Q&A. Okay, let's move on to the main part, which is mentioning some problems with the best system approach and scientific practice. So I gave you a few problems. I gave you a list here just to let you know that first, I'm not claiming that this is a complete list. This is a list adequate for a 1 hour long talk at the center. You can carry on after this talk, your second part of homework. The second reason why I gave you this list is because if you look at this quite carefully and if you're familiar with the critique of the best system approach, you will see that some points look familiar. So for instance, problems with simplicity or problems with inter-system comparisons, as I will show, take a new form when you actually consider equations. And I think that this form is interesting enough to show you this. So let's move on to the first problem, which is the problem with idealizations. And again, general philosophers of physics have read a lot about this. I'm sure that you have your own favorite paper about idealizations. My favorite paper is a paper by John Norton. First, because he's correct. Second, because in his paper, he famously makes a distinction between idealizations and approximations. As I will try to argue to you, once you make this distinction, there are some different ways in which both idealizations and approximations fail to be laws on the best system approach. So how does John Norton understand idealizations? According to him, idealizations are systems distinct from the target physical systems, such that some of their properties are an inexact description of the target systems in question. So crucially, idealizations are systems. In contrast to approximations, which are propositions that in principle aim to accurately describe a physical system. So I do want you, we'll show some examples, see some examples so it will become clear soon. Right now, I want you to notice two things. First, idealizations are systems, approximations are propositions. Second, idealizations are not trying to be the target system. They are from the very design meant to be inexact descriptions, while approximation are trying to be, are aimed to accurately describe a physical system. By the way, I think that I'm actually quoting John here, so I should put quotation marks here. Page 2009, if you want to check. So let's consider the most general example of an idealization. So crucially, again, idealizations are laws. So don't be misled by this equation, because idealization is a system of point-like particles with perfectly elastic collisions, yada, yada, yada. And indeed, physicists quite often talk about the ideal gas law. I'm sure you've all seen it. Again, doesn't matter what it means. P is pressure, V is volume, and so on and so forth. What is the problem here? Well, the problem is that there are no local matters of fact about idealizations from their very definitions, because again, they're not even trying to be target systems, because idealizations are from their very design fictional systems. Now, as I told you, I started thinking about these things during my undergrad, and since then, Toby Friend published a paper on how to be a humanist, I think, about idealist systems, and it's a very interesting paper. He does understand idealizations more like John understands approximations, but he uses an example of ideal gas law, so that's why I want to address his response right now. So his solution is the following. He employs the notion of the so-called super laws, which he takes from a book by Nancy Cartwright, and he says that for every idealized law, there exists a corresponding super law. And by definition, the super law first provides a more accurate description of the actual physical system, and second, it reduces to the idealized law under appropriate substitutions. Again, we'll see this on an example in a second, but for now, let's note that therefore laws such as the ideal gas laws are meta-ized, that's the term he uses, so they do not describe the Humean mosaic itself, okay? How does it work? Well, he considers the ideal gas law, and he says that the super law of the ideal gas law is the van der Waals equation, again, probably quite familiar to you. And if you look carefully, you basically get like two corrections here if you compare 7 and 8. So A stands for a parameter that accounts for intermolecular attraction. You remember we assumed that in the ideal gas, particles do not interact with each other. And then B is a parameter that accounts for the finite size of molecules. Basically, when physicists say that size is finite, it means that it's not point-like, it has size, roughly speaking. And we can check that when we compare it against the two criterion mentioned by Toby Friend before, we can see that it is indeed a super law. So first, it does provide a more accurate description of the actual physical system, precisely because it has just two corrections. And second, it really does reduce to the ideal gas law for A equals 0, B equals 0. So you can see this quite easily. If A equals 0, this term disappears. If B equals 0, that term disappears. And then 8 becomes 7. I think it's a very interesting way of responding to the problem of idealizations in Humanism, but I do see some problems with this account. So the first problem I have is that what guarantees that for every idealization law, there exists a super law? And to be fair, Friend does acknowledge this problem in the summary of his paper, and he says that we may not have an epistemic access to the super law, but surely it exists. It is not very clear to me why it does, and especially in the context of scientific practice, when I want to say, let's consider laws that are actually used by the physicists, I'm not convinced by this point. The second two problems are quite related. Okay, even if you buy into the story, how do you explain that physicists use both the ideal gas law and the van der Waals equation, and they consider both as laws? Surprisingly, the ideal gas law is incredibly successful in predictions of actual physical systems, and it's really often used, especially by the engineers. And related to this somewhat is that the solution with meta-ized laws seems to be a bit ad hoc. So it seems that we need a lot of additional structure to justify a fairly straightforward point in physics, namely that both van der Waals law and ideal gas law are laws of nature as physicists perceive them. And finally, I think that in a sense, Friend's solution proves my point, because he says that idealization laws are not laws of nature. Again, they don't describe Humean mosaic. They are meta laws instead. So they are not laws of nature. Thank you, Toby Friend. Okay, so as I promised you, idealizations and approximations, I think, fail to be laws of nature on the best system approach from two different reasons. So let's see how it all looks for approximations. And to do this, consider an example of Einstein's equations. Again, you don't really need to understand the details. On the left-hand side, we have Einstein's tensor, which corresponds to a space curvature. On the right side, we have energy momentum tensor that tells us about mass distribution. It's not very important. What is important is that if you take a degree in theoretical physics, at some point in your course of general relativity, you'll be asked to do something that is called taking Newtonian limit. So it turns out that if you take the G mu nu metric in general relativity that is in general curved, you can actually approximate it by a flat Minkowski metric eta mu nu, perturbated by some small factor. And then if you add a few more assumptions, and then if you do mathematics, you perform something that is called linearization, which again is super standard procedure that you do as a part of your physics degree. And magic happens. It turns out that you can actually recover at the very level of formalism. Like, forget about your metaphysical commitments. On the level of formalism, you get the Poisson equation, which basically describes the Newtonian gravitational potential sourced by the mass density rho. And then the second equation here is Newton's second law. So here the problem is that there are no local matters of fact about approximations, because even though approximations aim to describe actual physical systems, as we remember from Norton's definition, they do not do this exactly. So if you take it literally that these are laws of nature, there are no local matters of fact about this, because there are local matters of fact only about 9. There is a way to defend the best system approach from these kind of issues, but the solution is the same as the solution to the next problem. So let's move on to the next problem, which I called the lack of isolated systems. So take your favorite law of nature. To look at more friendly, I chose something that you probably all know. So let's assume that Newton's second law is exactly correct. The problem is that, again, there are no local matters of fact that correspond to this law, because there are no perfectly isolated systems. And what do I mean by this? If you take a body moving with acceleration under some kind of force, and if you measure the force, measure acceleration, measure mass, and you plug it into the equation 13, you will not get most likely exact equality here, because this body, if it's an actual body in the physical world, is also subject to air resistance and maybe some quantum effects and so on and so forth. So I'm not the first person to point out this difficulty, and people are working on this, also something that is called the approximate best system accounts. And on these view, you are meant to assume that candidate laws, namely elements of true deductive systems, only approximately describe local matters of fact. And these authors developed this account. I think it's worth trying to make it work, but my problem is the problem with vagueness. So consider a system that I described just now. You've measured mass, you've measured body acceleration, you've measured the force. And it turns out that you basically get acceleration of 1.2. So if you plug it into the equation, you get that 1 equals 1.2. Is it approximate enough? It's like 20% off. Is it good enough? Is it not? If you say no, I can keep asking you further. What if you substitute, you get such a result, and so on and so forth. So, the most generic vagueness objection. Okay, let's move on to some problems with the best system approach, which are already familiar to you, probably from the literature, but I think take new form when you consider laws as equations. So consider 2 formulations of the Gauss law, the first out of 4 famous Maxwell's equations. In the beginning, I told you that Maxwell didn't know the notation with divergence operator. So when you look at his original papers, they look more like 15th. Again, doesn't matter what exactly it means. What is important here is that they are written in different form. Like when you don't know the difference of divergence operator, these two looks like 2 completely unrelated things. So what is the problem? Well, now consider 2 candidate best systems, and they're all exactly the same, but one contains equation 14 and the other one contains equation 15. So that's how it's meant to look. And now the question is, which one is the best system? Obviously, you do have a problem with the standard of simplicity because they have the same strength. This is literally the same equation that has the same predictive power. And now, depending on what standard of simplicity you'll choose, you'll get different answers. So when you look at this, to me, S2 looks more complex, like less simple. because you have more characters. So if that's your criterion, then you answer that it is S1, which is the best system. This is obviously very naive, because actually, if you're Maxwell, you're looking at S1, scratching your head, being like, what is this triangle here? So to help Maxwell, maybe you should add to the set of your, to your deductive system, maybe you should add the definition of divergence, right? And then if your standard for simplicity is not in terms of counting characters, but counting theorems of your system, then actually S2 is the better system here. Okay. Another very typical problem that is raised on the best system approach is the problem with inter-system comparisons, which is most often illustrated using the riddle of induction formulated for a completely different reason. We all know it. An objective is green if and only if it's observed before the year 2025 and it's green, or else it's not observed and it's blue. Analogical definition can be provided for Bleen. And now consider a language in which the predicates green and Bleen are simple. And by this, I mean that predicates green and blue are defined as observed before, yada, 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 in terms of Bleen and green, etc. And then in this language, sentence all emeralds are green will be more complex than in our natural language, where green and blue are simple. And I think that, so the problem is that there is no correct God-given language in which laws of nature should be expressed. As we'll see, David Lewis believed that there is, but that's on the next slide. I think that this objection takes a new interesting form when you consider actual laws as equations. So you can reformulate this problem instead of Grew and Bleen in terms of our former example of Gauss' law, right? So one may ask, like, why have I said that we should supplement this exposition of Gauss' law with the definition of divergence operator? Well, I said that it is for Maxwell. Maxwell is dead. We don't have to care about this. Rather than, for instance, define this explicit form with coordinates x, y, and z defined in terms of the nabla, right? Why? We don't really have a good answer. The answer of Lewis given to the original problem was that we should choose the language of natural properties. And I think that it leads to some further issues with the best system approach. So consider yet another formulation of Gauss' law. There is a circle here missing, doesn't really matter. If you are put off by the form of this equation that's deliberate, you're meant to look at this, look at my explanation here that ds is the differential vector element of the surface S, and you should just start scratching your head being like, hang on, like what is the natural property that corresponds to the S and the omega and so on? This is everything I have to say about this. I don't know how it should work. Maybe it can. Please come to and talk to me if you think that you can actually find natural properties that correspond to such elements. And because there are like elements of this deductive systems, because they're part of this language, according to Lewis, they should correspond to some natural properties. Okay, and the final problem I wanted to mention is the problem with units. I promise this is the last formulation of Gaussian law that you'll see today. And it's basically the same one, but we have it expressed with different units. So epsilon 0 is a constant. Of course, like 4 pi is also a constant. So you can define epsilon 0 as a 1 over 4 pi. So the difference between 17 and 18 is, again, only in the choice of units. And this is a very similar problem to the one before, so I'm not going to repeat myself. I just wanted to mention that maybe there is I kind of mentioned the solution as a joke, but maybe there is something to this. So physicists sometimes talk about natural units. And I'm really waiting for someone to take this seriously and see whether actually natural units are natural in the sense of natural properties or natural kinds as people talk about them in the philosophy of metaphysics. Last point used to be an objection, and then I realized that I don't know my logic well enough. But just to flag to you some problems that you may have if you care about your logic. So I started by saying, well, you know, David Lewis says that laws of nature are elements of deductive systems. In principle, you can have expressions from algebra as part of your deductive systems if you believe that algebra is a formal logic, a formal language. For various reasons, you may want to prefer to have your theories expressed in, for instance, first order logic. There is probably a reason why lots of philosophers of laws of nature do use, after all, first order logic to give examples of laws of nature. Or maybe you want to use like raw calculus if you want to be super faithful to scientific practice, as I called it. Well, if you go for the second option, so if you choose algebra, differential geometry, and so on, the question is, are they really formal systems? And I've talked to a few logicians that I know, and the views vary. So some people think that they're not formal enough. Some people think that they are formal enough. So just, you know, go and think about this. And if you go for the first option, like if you want all of your physics to be rewritten in first or higher order logic, I admire you. There is this group of Hungarian physicists and philosophers who rewrote huge chunks of general relativity into first order logic. I think it's really admirable. The question is, how far can you go with this? The second question is, isn't it too detached from scientific practice? And I even went back to this paper and read their introduction to check why are they doing this. And they are quite explicit that it's not because they think it will be easier or more plausible to do GR in first order logic, but they think that it can help us understand logic better. Roughly speaking, that's my understanding of what they're saying. So this is not a problem per se, it's just something for you to think about. Okay, so let's wrap it up. I presented several arguments for incompatibility of the best system approach with scientific practice, and this is not an exhaustive list. However, we all took our undergrad course in logic, so we know how counterexample work. Even if you disagree with almost all of my problems, but one of them is correct, you are bound to reject the best system approach. Obviously, as long as you assume that philosophical accounts of laws should reflect how laws are used by scientists. Now, you know, I woke up this morning, it was sunny, it's Friday, I thought I can't end my talk with such a negative conclusion. So should you really reject a best system approach? And I think that there are a few ways out of this problem. Because I mean, it is a bit concerning, like the structure of this talk I gave, it's like a hydra, right? Like if you reject one objection, you can come up with another one. So I think we need to think about a more systematic way of defending the best system approach. So strategy number one is to say, well, physicists and philosophers do talk about laws of nature. They use the same word for this, but actually they're referring to two different entities. That's not an uncommon attitude in philosophy of science, but then you have a problem with explaining what are they if they're not the same thing, right? And why do they work? Because laws of nature have huge explanatory power, yada, yada, yada. If both laws of nature of physicists and of philosophers have the same characteristics, how do you justify that they are different? Strategy number two is that, well, maybe philosophers do not have to worry about examples from science. And I think it's probably one of the most common attitudes you can take. So sure, physicists do their own stuff, but actually laws of nature are thoughts of God. They are those very deep dispositions. We don't need to worry about what Feynman said in his handbook. And that's fine. But then we lose the whole relevance of philosophy to scientific practice, which I think is quite trendy nowadays. The third strategy is something that I was trying to do, and this is why it took me so long to write this paper. Basically, try to take all problems I've mentioned and then all modifications of the best system account, and then try to develop the ultimate, the better best system account by gluing them together. And I said, but then you create a monster. It was a very long paper and it was dreadful, and I just left it and kept my problems here. So just to end you with a very general conclusion at the end, I think that maybe the way to go is to take half of what Lewis said and reject the other half. So as I promised you, I was telling you about David Lewis's account of laws of nature as consisting in two elements, Hume and mosaic, and then this whole definition of laws of nature as deductive systems. Maybe accept Hume and mosaic and reject the bit where laws of nature are required to be parts of deductive systems. I have no clue what laws of nature should be then, but it seems to me that lots of my colleagues, well, philosophers of physics who are in favor of humanism, and you see them mentioning humanism in lots of places, they usually talk about Hume and mosaic and how it's relevant to their work. They rarely talk about the balance of simplicity and strength, because I think partially it leads to many issues. And now I really end it. Thank you.
We'll take a few minutes break and then we'll have plenty of time for questions.